Hey everyone, and welcome to Pod 4 Journal Club. You know, our oceans are just immense. They're mysterious, they're beautiful, and they are absolutely vital to life on Earth. But how much do we actually see of what's happening in them? Well, today we're breaking down a fascinating new paper about an AI that's being taught to see the ocean like never before. This could completely change how we monitor and protect our planet's most critical resource.
So, here's how we're going to tackle this. First, we'll get into the huge challenge scientists face, what we're calling the ocean's data problem. Then, we'll peek under the hood to see how this clever AI actually learns. After that, we'll check out its report card to see how it did on some really tough tests. But we'll also talk about its limitations, where it still has some room to grow. And finally, we'll zoom out and look at the big picture, what having smarter eyes on our seas really means for all of us.
All right, let's dive right in. Now, to really appreciate why this new AI is such a potential game changer, we first need to understand the sheer scale of the problem it's designed to solve.
Okay, get this. Our oceans cover more than 70% of the planet. They are absolutely massive. But our ability to actually keep an eye on what's going on inside them is, well, it's incredibly difficult and, honestly, surprisingly limited.
It's such a fundamental question, right? Because, as it turns out, our view is frustratingly blurry, and the AI models that we've had up to this point, they haven't really been much help.
So what makes this so ridiculously hard? Well, it really boils down to a few key issues. First, sending ships or people out to take measurements is super expensive, and you only get these tiny little snapshots of a vast, constantly moving system. But second, and this is the really wild part, most of our best AI vision models are total landlubbers. Seriously, they're trained on pictures of cats, dogs, and city streets. So you show them the ocean with its shifting waves, its ripples, that glint from the sun, and they get totally confused. And the last piece of this puzzle, there just isn't a big library of labeled ocean images to teach an AI with in the first place. And this is where the researchers behind this paper, the creators of OceanMAE, got really, really creative. They came up with a new way for an AI to basically teach itself about the unique physics and visuals of the ocean.
Okay, so before we go any deeper, let's nail down a key concept here: self-supervised learning. The best way to think about it is like this. You let an AI loose in a giant library full of books, but with no instructions. Just by reading everything, it starts to figure out grammar, context, and how sentences are built, all on its own. In this case, the books are just tons of unlabeled satellite pictures of the ocean. The specific method they're using is called a masked autoencoder. I know, it sounds super technical, but the idea behind it is actually brilliant. Imagine playing a high-stakes game of fill-in-the-blanks with an AI. You showed a picture of the ocean, but get this, you black out 90% of it. The AI's only job is to fill in all the missing pieces. Now, to do that successfully, it can't just guess. It is forced to learn the deep, fundamental patterns of what water and waves and coastlines actually look like. And this is what that process looks like in practice. See on the far left? That's the satellite image, but most of it is just gone, totally masked out. The first bit of the AI, the encoder, studies those few visible patches. Then, the second part, the decoder, takes that tiny amount of information and tries to rebuild the entire picture on the right. It's an incredible challenge. But OceanMAE has a secret weapon. And this is it. This is the secret sauce. This is the twist that makes this AI so special. It isn't just looking at the pixels in the picture. It also gets fed real-world data for context. Things like water depth, how much chlorophyll is present, how clear the water is. This helps it understand why the ocean looks the way it does. It helps it tell the difference between deep water and shallow water, for instance, even if they might look similar from a satellite. This whole thing happens in two main stages. First, you've got the pre-training. Think of this like the AI's general education. It just learns the fundamental patterns of the ocean by studying 100,000 unlabeled images. Then comes the second part, fine-tuning. This is where you take this generally ocean-smart model and give it specialized training to do a specific job, like hunting for oil spills. So, after all this clever training and self-teaching, the million-dollar question is, did it actually work? Let's get to the results and see how it stacked up against some real-world challenges.
The researchers really put OceanMAE through its paces. They tested it on 3 critical and very, very difficult ocean monitoring tasks: trying to map the depth of the seabed, spotting floating garbage and marine debris, and identifying nasty pollutants like oil spills. First up, spotting floating trash. So here, they pit OceanMAE against the standard AI model that's often used for this kind of work. And the results? A pretty clear win. If you look at pixel accuracy, which is basically just the percentage of the image the AI got right, OceanMAE jumped from 69% to 77%. That is a really significant improvement in telling the difference between what's trash and what's just, a wave.
Now, the results for finding things like oil spills were even more impressive. I mean, here it went up against the previous state-of-the-art model, and it just outperformed it across the board. That MIO score, that's a metric for how precisely the AI can draw the boundary of a spill, it jumped by over 6 points. And the macro F1 score, which shows how well it identifies different types of pollution, also got a huge boost. So in plain English, it's not just more accurate, it's actually smarter about what it's seeing.
And you don't even need the numbers. This image illustrates the difference perfectly. On the left, you've got the raw satellite image. In the middle is the prediction from the older baseline model. You can see it's kind of messy. But look at the right. That's OceanMAE. The boundaries are so much sharper, there's way less noise, it's just a much cleaner, more accurate map of the pollution. The visual proof here is really compelling.
But, good science is rarely about simple slam dunk wins. The results also uncovered some really important subtleties and limitations. And honestly, that's where things get even more interesting. So let's talk about that third task, mapping the seafloor. Here, the results were, they were more mixed. The benefits of using OceanMAE weren't quite as obvious. Its performance really seemed to depend on the specific coastal area, things like how clear the water was, what the seabed was made of, and also how much good labeled data they had for that specific spot.
To really figure this out, the researchers did this fascinating experiment. They tested OceanMAE against a version of itself that didn't get that extra physical ocean data. And the result? Well, OceanMAE, with all its special context, was definitely better on overall accuracy. But, and this is a great piece of science, the simpler model actually scored a little bit higher on one specific quality metric. It just goes to show, there isn't one single best solution. There are these complex trade-offs, and the right tool really depends on the exact problem you're trying to solve.
And the authors themselves say as much. They wisely conclude that this is not a one-size-fits-all solution. The best approach, whether to use this powerful pre-trained model and exactly how to fine-tune it, really depends on the specific job you're trying to do.
Okay, so what does this all add up to? Let's zoom out and really look at the big picture for how we understand and hopefully protect our oceans.
The bottom line is this: OceanMAE represents a powerful new path to get around the ocean's massive data problem. By teaching itself on unlabeled images, it gives us a foundation for a whole new generation of tools. Tools to track pollution, to spot plastic waste, to map our vital coastlines. And maybe most importantly, it's a huge proof of concept for a bigger idea. That to truly understand the Earth, we need to build AI that is fluent in the language of Earth science, not just the language of the internet. Work like this really just opens up a whole new world of possibilities for monitoring the health of our planet. And it leaves us with a really powerful question to think about. Now that we're building these incredible new eyes to see our oceans more clearly than ever before, what is the first, most urgent problem we should ask them to solve? That's it for this Journal Club. Thanks for tuning in.